Okay, so if we kind of look at where we were yesterday, and I can tell you guys don't have your notes out yet. I'm just going to have a little best part of my day. You guys, in the wintertime, like this time of year, I have my morning cup of coffee with a lit Christmas tree. And I do the crossword puzzle with the Christmas tree on and a cup of coffee. And my mom made me a Christmas quilt. And I'm just saying, can you top that? You have your morning cup of coffee, you're doing a crossword puzzle with a Christmas quilt.
That is really cozy.
It was like, and I had my slippers on and a warm hoodie. Yes.
Would there be, because I did this so I have to take the midterm early, would there be any way I could go in the hall and start the other notes?
Yeah.
Okay.
Okay, y'all. So yesterday what we do, we just kept taking a sample, right? And as we took that sample, when we look at this, you guys, notice I'm not scooping, I'm just talking about the bin itself. Does the bin itself have a set probability that is red? Okay, so if I were to say the proportion of the entire bin, while I don't know what it is, that doesn't mean it doesn't have a value, okay? So it's a question mark, but are you with me that it is a constant? It's not like this bin only has 1% that is red. But the reason we got all these different percents that are red is because this is a sample, and what do we know about samples? We didn't really...
Inaccurate.
They are not perfect. They have variability. So, if I were to say draw a picture, we could even start a dot plot of all of our different samples. So the 0.773 might be here, and that 0.864 might be here, and the 0.73 might be here. And I could do this again. And let's see, guys, this one is 15 out of 22. Which is going to be, I don't know, here-ish, 0.68. Mm. And I could do it again. Same thing. And I could do it again. Oh my God, same thing. This is kind of crazy. Do you guys get my point here? This one is only 16, so another 0.73. And so every time we take a sample, the samples are variables. The percent of the samples. Because the percent of the samples changes depending on which sample I take. And what it boils down to, and we're going to talk about this over and over and over again, samples are not perfect. They have variability. So the whole point of what we're going to do in Unit 5 is going to be lay the groundwork, because we rarely know what percent our population is. But that just because samples aren't perfect, that doesn't mean they're unpredictable. And so this unit is going to be all about learning the predictability of what we know about samples and how they behave, so that in the next units we can take a sample and generalize it to our population. So we're going to spend a lot of time on normality. So I want to do a real quick review of normal distribution stuff. Okay. So let's go ahead and say the weights of hazelnuts are normally distributed with a mean of 1.34 grams and a standard deviation of 0.25 grams. You guys, I totally made up those numbers. I'm certain that doesn't surprise you. Okay, so if I ask you what is the z-score of a hazelnut, that is 1.56. It's possible we don't remember what a z-score is. Is that possible?
It is true.
Okay. A z-score is the number of standard deviations from the mean. So the first thing you're going to do is figure out, well, how far is that point from the mean? By taking 1.56 minus the mean. So I'm going to write down this formula. X minus the mean divided by, so that tells me the distance, and if I want to know how many standard deviations is that, I would divide by the standard deviation. Can somebody help me out here? So we could say that hazelnut is 0.88 standard deviations above the mean. And guys, remember we kind of talked about, well, how many standard deviations above the mean or below the mean is kind of crazy. And our general rule of thumb is anything more than 2 standard deviations away would be kind of, I don't want to say absurdly away from the mean, but definitely atypical. Okay? All right. Now, what is the weight of the 30th percentile of the hazelnuts? Well, we know that they're normal. We can go ahead and describe the mean and the standard deviation. And if something is the 30th percentile, I'm going to start shading, and I just want you guys to tell me when to stop.
Stop.
Maybe a little bit further. Maybe here. Is that okay? And do I know, I don't know the boundary. What I know is that I'm stopping where that area is 30%. So, do I have an upper and a lower to put this into normal CDF?
Isn't it the inverse?
Yeah, I don't have that upper. In fact, I'm trying to figure out what is that upper boundary. So, what I have is the area, so I'm going to choose inverse norm. I have no idea what this answer is, guys. 1.21 grams? Am I right that you guys wanted this little quick review of the normal distribution because we're going to be using it a ton? A ton. All right. In what range of weights can we find the middle 90%? So, of course, I'm going to label my mean and my standard deviation first. Okay, and that middle 90% would be kind of like here-ish, yes? And we would know that the area of this section is, in fact, 0.90. You guys, what does that make this area? The red area. 5%. And then, as is the, the purple area. All right, so let's go ahead and say I'm trying to find, I'm going to describe these as XL and XU, just standing for the lower boundary and the upper boundary, okay? If I want to find XL, what area should I tell the inverse norm? 0.05. Because the area to the left of XL is 0.05. I don't know what the answer is. Again, you guys with your fancy calculators are smarter than me. I'm sorry? 0.928, okay. What area should I give it for XU? I should give it the area to the left of XU, which I'm going to go ahead and highlight here. You can't really see it. Are you guys with me? That pink area is the one that's to the left of XU. What area is that? Yeah. I got to do 0.95. And 2 point something.
1.75.
1.75? I'm off by that much. So between 0.928 grams and 1.75 grams. Now, if you have one of the light up calculators, the thinner ones, you could also have done inverse norm of 0.9 and highlighted the word center. And it would have gotten you that as well. How are we feeling so far? Okay, this last one's probably the hardest one. Let's go ahead and take a look. The running times of movies are normally distributed with a mean of 102 minutes. Uh-oh, the standard deviation is our question mark here. Is everybody with me? Now I could even, I can go in and highlight a lot of things on this. And I say, I'm going to make this boundary A for Aladdin. Is Aladdin like a relatable movie to you guys? Like, did you watch it as a kid? Okay. I might have to switch this out with a different movie at this point.
People watched Aladdin. Who didn't watch Aladdin?
Have you never seen it?
I've seen it. I mean, I guess I've seen it probably one time.
You guys, I saw it in the theaters.
And
It was pretty killer.
1996,
Have you watched it?
and 94, 92,
Dude, I just,
87.
I think it went, Little Mermaid came out in 87, and then Beauty and the Beast came out in 90, and then Aladdin was 92. I'm pretty sure that was about the time frames of those. I'm not saying that Aladdin is one of my favorite movies of all time, because it is my favorite movie of all time.
I mean,
It's actually not my all-time favorite. That's an impossible question. Nobody has an all-time favorite movie. Am I right? If I were to ask you what's your favorite movie of all time, everybody goes, I hate this question. Because everybody can make a list of 4 or 5 that are all mood specific, right? Mm-hmm. If I'm in a bum around my house and play games on my iPad mood, I want to watch Avengers, okay? But if I'm in a Christmas spirit mood, I want to watch Miracle on 34th Street. Or It's a Wonderful Life, which I haven't watched yet this year. You guys catch my drift here? Yeah. Does anyone know how to do this? It's feeling pretty icky, huh? Because your calculator pretty much needs to know that standard deviation, doesn't it? Right? Okay, so what do we do when we don't have enough information?
Get really sad.
What we're going to do is there's one other piece of information we haven't talked about yet. We have talked about it, but it was a long time ago. I'm going to draw a new normal curve. And this normal curve is going to be the normal curve of z-scores. Not the actual values, but the value z-score. And the thing that's really, really lovely about z-scores is they always have the same mean, which is 0. And they always have the same standard deviation, which is 1. And I can say, what is the z-score of the 23rd percentile? Have you guys ever noticed that if you haven't used the normal distribution in a while, it always goes back to that default 0 and 1? This is why. This is the standard, what we call the standard normal curve, because it's the, curve of the standardized scores. And so What z-score is it? I'm certain it's negative.
-0.74.
-0.74 sounds about right to me.
What does that mean?
That means that anybody who is the 23rd percentile in anything is 0.74 standard deviations below the mean. And whether we're talking about height, or the weight of hazelnuts, if you're going to be the 23rd percentile in a normal distribution, you'll always be 0.74 standard deviations below the mean. Well, this becomes really helpful because if we were to say, well, wouldn't z equal Aladdin minus the mean over the standard deviation? And if we start thinking that through, well, we know the answer to z is negative 0.74. We don't know Aladdin, right? Do we know the mean? Oh, we do know the length of Aladdin, don't we?
Yeah.
It's 102. The mean,
92. The movie's 92.
thank you. And we have all the information we need now to solve this. We only have one variable, yeah? So I'm going to do two things. I'm going to multiply both sides by sigma to get it out of that denominator. And I'm going to do 92 minus 102 is negative 10. So I'm really just doing negative 10 divided by 0.74. Divided by negative 0.74. And we get a standard deviation of 15.51.
Or 13.
13.51, thank you.
I got 13.5.
That probably comes from rounding somewhere. As long as you're close, you're fine. How we feeling? All right. From here.